Hello and welcome. Today we embark on a journey to the very edge of human understanding to confront one of the universe's deepest and most baffling mysteries that is known as dark energy. For decades, we have lived with astonishing revelation that our universe isn't just expanding, it is speeding up, pushed towards by an unseen, unknown force we call dark energy. It's been described as the cosmic constant, an unchanging engine driving the galaxies apart. But what if our understanding has a crack in it? What if this immense, invisible force, the very energy of the cosmic expansion, isn't constant at all? What if dark energy is weakening? Recent groundbreaking studies peering through the light of distant supernovae suggest precisely this. It's a finding that could profoundly reshape our cosmic narrative, altering our predictions for the universe's ultimate destiny. So, join me as we explore these cracks in the cosmos and ask if the dark energy is weakening. To truly grasp the magnitude of this new discovery, we first need to understand the cosmic landscape as we thought we knew it. For most of the 20th century, cosmologists believed the universe's expansion set in the motion by the Big Bang and must be slowing down due to gravitational pull of all the matter within it. It was like throwing a ball into the air. Eventually, gravity pulls it down, or at least slow it down. Then came 1998, a pivotal year in the cosmology. Two independent teams of the astronomers, the Supernova Cosmology Project and a High Z Supernova Search Team, were using distant exploding stars called Type 1a supernova to measure the rate of universe's expansion. They expected to see it decelerating. Instead, to their utter astonishment, the data showed the opposite. The expansion was accelerating. Universe wasn't slowing down, it was speeding up. This mind-bending discovery earned Saul Perlmutter, Brian Schmitz, and Adam Rees the Nobel Prize in Physics in the year 2011 and introduced us to the biggest mystery of the modern physics known as dark energy. So, what is dark energy? Well, that's the multi-billion dollar questions. We know what it does. It's responsible for this accelerating expansion, but we don't know what it is. It's not matter. It doesn't clump together like galaxies or stars. It's not dark matter, which is another mysterious substance that exert gravitational pull, helping galaxies hold it together. Dark energy, conversely, seems to exert a repulsive force pushing things apart. Current observations suggest that the dark energy makes up to about 68% of the total energy density of the universe. That's an astonishing figure. Regular matter, the stuff we can see and touch, things like stars, planets, ourselves, account for only 5%. Dark matter makes up to about 27%. The vast majority of our universe is made of stuff we can't see, we can't touch, and barely understand. The simplest explanation for dark energy has been something called the cosmological constant, often represented by the Greek letter lambda. In Einstein equation, the Einstein actually introduced lambda into the equation of general relativity to achieve a static universe, something he later called his biggest blunder after Edwin Hubble discovered the universe was expanding. Ironically, this blunder might have been a stroke of genius. And this is for a totally different reason. The cosmological constant implies that the dark energy is an intrinsic property of the space itself. As space expands, more space is created and therefore more dark energy is created, maintaining a constant energy density. This constant energy density leads to a consistent accelerating push. It's a very elegant idea, but it comes with its own problems. Theoretical calculations for the energy density of the empty space are astronomically larger than what we observe by a factor of 10 to the power of 120. This is arguably the biggest discrepancy between theory and the observation in all physics. This massive theoretical problem, combined with the fact that we have no direct way to detect dark energy, has kept cosmologists searching for alternatives. Could dark energy be something more dynamic, something that changes over time? And this is where the new supernova study comes in. To probe the nature of dark energy, scientists turn to cosmic beacons. Type 1a supernova. Imagine trying to figure out how a fast car is moving away from us in the dark without a speedometer. If you knew how bright its headlights truly were, you could gauge its distance by how dim they appear. The dimmer they are, the further away the car is, and the faster it must have moved to get there. Type 1a supernova are our universe's standard candles. These are not just any stellar explosions, they occur when a white dwarf star in a binary system siphons off matter from its companion. When it reaches a critical mass known as the Chandrasekhar limit, it triggers a runaway nuclear fusion reaction, causing a colossal, predictable explosion. Critically, these explosions all reach roughly the same peak intrinsic brightness. This makes them incredibly valuable tool. By observing type 1a supernova, measuring its apparent brightness and comparing it to its known intrinsic brightness, astronomers can precisely calculate its distance, and by also measuring the redshift of its light, how much light has been stretched by the universe expansion as it traveled to us, they can determine how fast that part of universe was expanding at the time of the supernova exploded. For decades, we have built a cosmic database of these supernova, essentially mapping the universe's expansion history over billions of years. Think of it like taking a snapshot of the universe's growth at a different ages. The latest and the most extensive of these survey is known as the Python plus analysis, which includes data from over 1500 type 1a supernovae. This is an incredible amount of data meticulously calibrated and analyzed. The traditional view based on the cosmological constant, which is lambda CDM model, predicts a specific smooth curve for how the universe's expansion rate should have accelerated over time. But when scientists meticulously process the Python plus data looking for the most subtle deviations, they found something intriguing. The finding published recently suggests that the universe's expansion might not be uniformly accelerating in the way predicted by the constant dark energy. Instead, there is a hint is statistical preferences for model where the dark energy has been weakening over cosmic time. It's like the cosmic engine, while still pushing, isn't pushing quite as hard as it used to. This isn't to say the universe is decelerating entirely, it's still expanding and still accelerating, but perhaps not with the relentless, unyielding force as we had assumed. The cracks appear when the data suggests that the distant past, dark energy influences might have been slightly stronger, and now in the more recent cosmic epoch, its repulsive push is a bit less potent. It's crucial to understand that this is a suggestion from a new study, not a definitive confirmed fact. The scientist community is now rigorously scrutinizing these findings. Could it be statistical fluctuation? Are there any unforeseen systematic error in our measurement, or is it genuine signal of a new physics? Scientists are exploring all possibilities. If confirmed, this would imply that the dark energy isn't simply a cosmological constant. Instead, it might be a dynamic field, often referred to as a Imagine an energy field that appears permeates through space, but whose strength and density can change over time. If dark energy is indeed quintessence field that is rolling down its energy potential, it would naturally weaken over billions of years. This would dramatically alter our cosmic models and open up entirely new avenues for research. So if the dark energy is weakening, what does that mean for the ultimate fate of our universe? Our current understanding based on the constant dark energy model. And this offers a few grim scenarios. Number one is the big rip. If the dark energy continues to strengthen or remain constant, it could eventually become so powerful that it would tear apart galaxies, stars, planets, and even atoms themselves in a horrifying big rip. Second is the big freeze, or it is also known as the heat death. If the dark energy remains constant, universe would expand forever, but at an ever accelerating rate, leading to extreme dilution and isolation. Galaxies would become so far apart that their light would never reach others. Stars would eventually burn out, black holes evaporate, and the universe would end up as a cold, dark, empty void. But if dark energy is weakening, these scenarios might change dramatically. If its repulsive force diminishes, the universe's acceleration could slow down considerably. It might eventually transition from accelerating to decelerating phase. In an extreme case, if the dark energy weakens sufficiently, gravity pull from all other matter in the universe might once again become a dominant potentially leading to a big crunch where the expansion reverses and the universe collapses back into itself. Much like the Big Bang in reverse, though current data makes this seems unlikely in near future. More subtly, even if it doesn't lead to a big crunch, a weakening dark energy would mean a less violent or perhaps a slower form of big freeze, as the expansion would be less aggressive over the very long term. These new findings inject an unprecedented level of uncertainty and excitement into the field of cosmology. They underscore how much we still have to learn about the fundamental force governing our cosmos. This research isn't just about tweaking the model, it's about potentially uncovering a completely new fundamental law of physics. We might be witnessing the first subtle hint of a dynamic cosmic field rather than a static one. What happens next? Scientists will continue to gather more data from even more distant supernovae. Upcoming missions like NASA's Nancy Grace Roman Space Telescope and Europe Space Agency's Euclid mission will provide unprecedented amount of data. Observing millions of galaxies and supernovae with incredible precision, this new data will be crucial in confirming or refuting the current hints of weakening dark energy. The theoretical community will also be busy developing new models of dark energy, exploring different forms of quintessence, and trying to reconcile these observations with quantum gravity theories. The interplay between observational astronomy and theoretical physics is how we push the boundaries of knowledge. The notion of the cracks in cosmos isn't a sign of breakdown in our science. Rather, it's a testament to its power. It shows that our models are constantly being refined, challenged, and improved as we gather more evidence. The universe isn't a static textbook. It's living, evolving mystery that continues to surprise us. For decades, dark energy has been a constant, a relentless force shaping the destiny of everything. Now, the whispers from distant supernova suggest it might be fading echo. This possibility opens up a new universe that is far from more complex, more intriguing, and perhaps more fragile than we ever imagined. Whether dark energy is truly weakening or if this is a trick of statistics, one thing is certain: the cosmos continues to hold its secret close. But Through the relentless curiosity and ingenuity of scientists, these secrets are slowly and painstakingly being revealed. The journey to understand dark energy, to truly map the fabric of space time, is far from over, and every crack in our understanding, any new questions that arises, only serves to deepen our sense of wonder for the vast, mysterious, and ever-folding universe as that we inhabit. So, friends, thanks for joining me on this cosmic exploration. If you have any questions, leave them in the comment section below. See you next time. Keep looking up. Until that time, bye for now.